Yeah. So we are at the last part of our course. That is, in the previous class, we were talking about the cash placement policies. Today, we are going to talk about the cash replacement policies. In the cash replacement policy, let me just recall you when the CPU send a request. When the CPU send a request for a cache line which is available in the cache or not, then upon this request received by your cache, if the frame is having the cache line, suppose, then we call this as your the hit. We call that as your hit. When there is a hit, okay, so then your the cache will send a reply gives the response to your CPU. So upon receiving this request, the response, CPU performs the computational, perform some computations, and the result will go back and write into the cache. That happens, right? That we have observed. If there is a miss, if there is a miss, okay, if there is a miss, then the request is forwarded to that the request of your cache file is forwarded to your main memory, forwarded to your main memory. In the main memory, okay, if that request is available, then that will be taken and that will load into fetch from main memory and load into the cache. And then after that, the cache will from this cache, that frame is responded back to the CPU. So this is the general, the caching strategy that goes. In that case, when the cache lines are fetched from your memory and load into your cache, after certain the load, if your cache become full, then some of the frames must be fetched, the evicted from this cache. So for that, what are different replacement policies are required that we are going to talk now. Okay. Is there any some questions? Are you able to hear me? Are you able to see the screen? Okay, Nathan. So are you able to see the screen also, Nathan? Okay, thank you. So we'll quickly finish it. Okay. So then comes to there are the common cash replacement policies that we are going to discuss. That the first in first out. Another cash replacement policy is the least recently used, and the third one is the most recently used, and many more policies are there. So if a cache miss occurs when the target set is full, when the target set is full, one of the way need to be evicted to store the cache line. So as we discussed that in the cache placement policy, are the set associative which combines the directed mapped cache and your fully associative cache. Then for every set zero, there are certain ways. Okay, suppose if there are two frames are there, means two way. If four frames are there, then we say that four ways. So like that, if any set is become full, suppose, then some of it must be evicted to store the cache line, new cache line. So your cache replacement policy that determines which way should be evicted. So the common the cache replacement policies that we say that first in first out means whatever the frame takes for the whatever the way first filled with the cache line. Suppose A is filled first, the first frame, then the second one, then the third one, then the fourth one. Then when it is filled, when the set is filled, then the first one is evicted and give that to the new one. So whereas in list recently used, the evict the way with the least recently used cache line, that the LRU assumes that if a cache line is not frequently accessed, then it is probably not needed in the future, so that must be evicted. Whereas in most recently used one, evict the way, here the way means way, or evict the slot, or evict the frame. Okay, so this with the most recently used cache. So in this MRU, it assumes that if a cache line is frequently accessed, then it is probably not needed in the future. And some other cache line placement policies are also there. But the most of the modern processors, they are following the least recently used cache replacement policy that we will discuss. So the which replacement policy works better, that depends on the applications, the memory access pattern. So again, the goal here is minimize the cache miss rates while do not increase the cache latency and cache complexity. So this modern processor typically use the policy that is based on the least recently used one, or but the non-LRU policies typically do not work well for the application's memory access pattern. So this LRU's assumption that fits the memory behavior of most real applications. So, however, implementing this LRU on hardware is very complicated, complex one. It is hard to implement in the hardware. So, therefore, the modern processors usually use the policy roughly based on this LRU, that is the approximation of your least recently used cache replacement policy is used. So the computer architects also tend to tweak this LRU policy to make it perform better. So for that, we'll just understand the basic principle and the step-by-step process of this LRU replacement policy algorithm. So this typically, the LRU policy requires a the additional memory unit, we call that unit as your queue. So this LRU policy requires maintaining a queue that is recording the recent access history of the way or the slot within a set. Okay, so for example, let's assume that the following access to the same set in a four-way cache, that is the cache line access like A, B, C, D, E, and B and F, and we have the cache. That cache is having one set. That set is having four ways. Cache is having one set. That set is having four ways. In these four ways, it is going to check, the LRU policy is going to check whether these accessed cache lines are available or not. If not, then the replacement should be take place based on the least recently used. So for that, once queue is maintained, that we call the LRU queue. In this LRU queue, this is the beginning of the queue, this is the end of the queue. When there is a cache miss, then that cache will be, that when there is a cache miss, then the cache will be from the memory, that cache line will be fetched, and that cache line will fetch from the main memory and store into your cache in a given way by following the set associated to placement policy, right? So upon the frame which is accessed, upon the cache line which is fetching from your main memory and loading into your cache, so as soon as it load into the cache, that requested cache line entry will be take place in the queue at the beginning of the queue to maintain the recording the recent access history of that way. Way 0 is used or not, way 1 is used or not. Okay, so let us see that in this example. So we have 7 caches. The cache axis is there, that A, B, C, D, E, and B, F. And we know that when initially the cache is empty, So upon the first cache line, that is A, is requested by your CPU, then obviously it is missing. When it missing, then it will be fetched from your main memory, and that will be loaded into your cache in the way following the set associative. In set associative, in the first set, whatever the first empty frame is there, that first empty frame is, or first empty way is allocated for accommodating this cache line A. So as soon as it is loaded in the cache, then its entry will be, it will be inserted. Its record, the recent access history record is inserted in the queue at the beginning of your queue. Okay, and as soon as the it goes with the next access B, when B is not there in the cache, then it is also missing. So that will be fetched from your main memory, and that will be loaded into your cache in the next first empty way of your set. And then the entry, once it is loaded, then the right shift operation takes place in the queue. So A is shifted from one position to right, so that at the beginning of your queue will be used for insertion of your B. So A will be shifted here, and this position is updated with the B. So then for the next access for C, it is not there in the cache, so it is missing again. So that will be fetched from main memory, and that will be allocated, that will load into your cache at the next first empty way of your set. And then the queue will be updated with A is shifted one position to right, then the B is shifted here, and here the C is inserted. For the next access D is not there in the cache, it is also missing, so that will be loaded in the cache. And once it is loaded, then the queue will be updated as uh, the queue will be updated as A is shifted to the last position, then B, C, and D. So upon the next access, that is E is not there in the cache, so it is also missing. When it is also missing, it must be loaded into your cache, but your cache is full now. Then the replacement policy takes. In that replacement policy, LRU says that the end of the queue is evicted. Okay, and that particular way is given for the new cache line. So in the queue, it is maintaining the recent access history. So where A is least recently used, so that will be A should be evicted from your way. And that way is used to accommodate the cache line E. Okay. So here your A will be evicted, and that will be used to accommodate E. So E will be accommodated at way 0. Okay. So then in the queue, the shift operation will be take place. So E will be inserted at the beginning of your queue. So then your queue record will be here. You will get the B, then your C, D, and your E is there. Okay. So next, it is going to, when it is accessing the B cache line, B is there in the cache, so it is a hit. Okay. Okay. So then after that, Once hit is there, that is responded, that B is given to your cache line, I mean the CPU, and then your queue will be updated. Your queue will be updated. So once it is recently used, it will be evicted and it will be evicted and insert at the beginning of your queue. At the beginning of your queue. So then it becomes you will get the B, E, D, C. So C become the end of the queue and B will be entered in the beginning of your queue. After that, it goes once that operation completes, then it goes and access the next cache line F. So F is not there in the cache. F is not there in the cache. So your F is missing. F is missing. When F is missing, then the least recently used cache line, that is C, is evicted from your queue, and that way is used to accommodate your F. So F will be loaded here, and from there your queue will be updated, like your D is shifted one position to right, E will be shifted one position to right, B will be shifted one position to right, and your F will be inserted in your queue, so that you will get the D, your E, B, and then F. So this method, we call it as your least recently used policy method. So next few slides that explains this, step-by-step process, okay, for your least recently used. But the problem here is to implement this, it is difficult on the hardware. So to implement this on hardware, or implementing this LRU queue with the shifting and the inserting in the hardware is fairly complex. So therefore, the computer architects look for simple implementation that are similar to the behavior of your LRU policy. LRU policy. So that is done by doing this some kind of approximation. The not recently used policy, which is similar to the behavior of your least recently used policy, but it is the approximation of your LRU. So to implement this one, the algorithm which is used to implement the behavior of your least recently used or non recently used policy, we call that as your clock adaptive replacement algorithm. Clock adaptive replacement algorithm. So in clock adaptive replacement algorithm, in that there will be a handle, we call the clock handle. Okay, so it will follow the clock cycle way. In that, whatever handle is there, that handle take care of which way is recently used and which way is not recently used. So as soon as the ways are been, then this clock handle advances to the next way, whether that way is used or not. Whether that way is used or not. So in this clock, the ways or your slots of your set are checked circularly similar to the clock, and each way maintains a used bit. Each way maintains a used bit to indicate if it is accessed recently or not. If it is accessed recently or not. For a cache hit, then the set the used bits in the cache hit, set the used bit of the way that goes a hit to 1. So if it is 0, if the used bit is suppose 0, that means that way is not recently used. If it is hit, then that is going to be used, so it will change its status from 0 to 1. Okay, for cache misses, visit each way or each slot clockwise to find a way that has a used bit 0. Find a way that has a used bit 0. That means that way is empty. So you can bring the cache line from your main memory and you can load in the cache in that way. So this way is then to victim for the eviction and replacement. And during this visit, during this visit, they set every used bit to 0 if it is 1. So let us see this with an example. There is in this the clock adaptive algorithm, it follows the clock handle we call. So clock handle starts with way 0 in the set. As we've seen that in the cache line, there is one set. That set is having the frames, okay, as we call the ways. So way 0, way 1, way 2, and way 3. And after that, it is having the data field here. In that, in way, like we have seen in the cache line, the first field is your tag field, second field is status, third field is the data. Along with that, in this car algorithm, it use the used bits. So that used bits 0 or 1. 0 means it is not used recently. 1 means it is used recently. So in this algorithm, there is one handle. It starts with way 0. As we know that in this set, it is going to load the cache line in the first empty slot of your set, and after that, next empty slots will be filled out by following the fully associative mechanism, right? So here in way 0, it uses two standards: used bit, and whether the data is there or not. So we'll just consider the same sequence of cache line accesses A, B, C, D, E, and your BF. So before access they start, the clock hand points to the way 0. The clock hand points to way 0, and always have always or your alls your ways in this cache line have used bits of 0, 0, 0, 0, 0, 0, 0. Okay. So then upon accessing, to access A, find the first way with a used bit of 0 in this car algorithm. So first way is your way 0, and that is used bit is 0 initially. So which is way 0 in this case there. So again A to way 0. So updates when A is fetched, because initially it is not there, so it is missing. So A is fetched from your memory, and that will load into way 0, and it change its the used bit from 0 to 1. Similarly, to access B, in this case, as soon as the cache line A is fetched from main memory and load into your cache and set the used bit from 0 to 1, your clock handle automatically advance to the next way. Handle advance to the next way. In the next way, that is way 1. In way 1, used bit is 0, and there is no data. So upon accessing the next cache line, that is B is not there in way 1, because it is used bit is 0, that is not recently used, and there is no data, so it is missing. When it is missing, it must be fetched from your main memory and stored into your cache. So that becomes your B. Once it is loaded in the cache, your used bit is set from 0 to 1. And once it is done, then it will advance to the next way, so that you can find the first way within a used bit that is 0 by moving the clock handle clockwise. So that is moved here. So way 1 has a 0 used bit. So again B to the way 1, assign B to the way 1, and update its used bit as 1. Similar, once it is done, then this your clock handle will be advanced to the next way. So our next access is yours. This is also missed. This is also not there. It is missed. So it will be find the first way, that is way 2. Okay. And the way 2 has the 0 used bit, and assign C to your way 2, and update its used bit to 1. Update its used bit to 1. Once it is updated, then it will be advanced, the 100 pointer advanced to the next way. Next way. So then for accessing D, for access D, find the first way of used bit, that is, you will find the 0 here. So then this particular way is assigned D to this way 3, D to the way 3, okay, way 3, and update its bit to 1. Update its bit, used bit to 1. Okay, and as soon as it is updated, here you can see that your cache is full. It is advanced to the next one. So the most important point in this CAR algorithm, when it is reached to the way 0 again, and after that, if anything is accessed and that is not there in the cache, in that case, in the very first clock cycle in the CAR algorithm, it is going to set all these ones to 0. Then it advance, it set this 1 into 0. After setting that, it will advance, set this 1 into 0. After setting this, it will advance and set this 1 into 0. After that, it will advance and find 0 used bit. Find 0 used bit means once your cache is full, your clock handle is start setting 0, the used bit to 0 in the first cycle. From the second cycle, it is going to load the newly accessing the cache lines, so to access each the cache is missing, that is not there in your cache, so it needs to find a replacement by visiting ways clockwise to find a way with a used bit 0. So visit way 0 first. It was the used bit is 1, so reset it to 0. Then visit to way 1 and used bit is 1, so it is reset to 0. Then way 2, it is reset to 0. In way 3, it is reset to 0. After that, it reached to when it is visiting the clockwise to find the way within the used bit of 0, it start finding used bit of 0. So when I visit to way 0, then it is used bit is 0 in this case. So find the victim and assign E to your way 0, and set its bit, used bit from 0 to 1, and then upon the next one, it advances to access the B, okay, a cache hit to the way 1 and update the way 1's used bit to your 0 to 1. So it's having 0, so that is set to 1. And then it advanced, then the clock handle advanced to the next way. In that next way, it is going to access the F. F is not there, so the cache is missed. So it needs to replace by visiting the ways clockwise to find a way with a used bit 0. So I visit this way to set, replace the C with your F and set that used bit as your 0 to 1. So this is the example of your CAR algorithm. So with this, you'd like to conclude this replacement policy is that in most of the modern processors, they use the least recently used policy. To implement this least recently used policy, it is implemented using your CAR algorithm. We call the clock adaptive replacement algorithm, which follows the not recently used cache lines. So then comes to the last part of your this cache design is your write strategies, right? Strategies. So as we know that CPU requested a word, it requests a the data word to perform certain operations. So first it go and check whether it is there in the cache or not, So cache is having the ways or frames or slots we can call in this cache. Okay. So if the requested data, suppose A is requested data word, if it is there, then there is a hit. When there is a hit, it is, respond to your CPU. CPU perform the operations. Let us assume that A is equal to 5. Okay, that data. Okay, so that is requested and responded to your CPU. So CPU performed the operation and set A is equal to, maybe it may set that A is equal to suppose 10. So that 10, this must be go and update in the cache, right? So that we call at your write policy, write strategy. Okay, so in this write strategy, if there is a hit, then how it is going to be right? If there is a miss, then how it is going to be right? So these are strategies we call the write strategies. So there are two types of write strategies are there. So that is what to do on write hit and what to do on write miss and how to do that. Okay, so for that, with the write hits, with the write hit. So in the write hit means what? When the CPU requested a data, the data is available in the cache and it is responded back. And when computation is done, it is going to write in the hit means that cache line is available in your cache itself. In that case, how to do that? To do that, we call that as your write back policy. Write back, when there is a write hit policy is there, we call the write request hit data in a cache, and write can be directed to cache instead of main memory. It is directed to the cache instead of main memory. So as I said, your CPU is going to write to cache only, not not in the main memory, because that is available here itself. So it is going to write in the cache only, not in the main memory. So the question is when to propagate the new values to the main memory. When to propagate the new values which are updated at A here is going to be propagated to your main memory, That we call the write back. The first policy is write back. The information is only written to the cache, and once your cache is full, and if this cache line is supposed to be evicted, when it is supposed to evicted, that time it is going to be right back into your cache, right back into your main memory. So the higher level caches and the memories are only updated when it is evicted. But before that, every time CPU is going to write within the cache itself, so it can write at the speed of your cache only. So the caches become the temporarily inconsistent with the higher level of your cache or memory. As we said, A is equal to 5 is taken, suppose, and that is updated as A is equal to suppose 10. That A is equal to 10 is updated in the cache itself, but not in the memory. Memory still have A is equal to 5 only as the previous one. So temporarily it is inconsistent, but once this cache line is evicted, it is going to update A is equal to 10 here. Right? So as we know that in that cache line, it is going to hold the piece of data. It is going to hold the piece of data in that cache line, this cache line, right? If this cache line is 64 bytes, then every byte is using one, every piece of this cache line is using 1 byte. So maybe in the first byte A, second byte B, third byte C, fourth byte D, and so on. So assume that A is equal to 5 initially in the cache line, B is equal to suppose 7 in the cache line, C is equal to suppose 8 in the cache line. So the CPU is requested first A, the piece of your cache line word, and that is updated to 10. Then second time it may access B, okay, and that B first A, then B, requested B, and that is responded by your cache, then requested C, that is responded by your cache. So those values may be after computation, the values may be changed, like B is equal to suppose 8 and C is equal to suppose 15. So all these are going to be right in this cache line again, So but in the main memory, the values are still A is equal to 5, B is equal to 7, and C is equal to 8. So once this operation is over, and if this cache line is no more required, so all these write operations combine together as single, and only once it is going to be write in the main memory, So that's why it says that it use the less memory bandwidth or power, because multiple consecutive writes may require only one final write to your main memory at the eviction. So multiple writes within the cache line can be merged into only one write. So this policy we call the write hit policy. In write hit policy, if the cache line is if the write to have the information is available within the cache line, we call it as your write back. Right. Okay. So the second strategy we call your write through. In the write through, whenever the CPU performs the operation, it is going to write not only in the cache, it also writes the same, parallelly in your main memory, Okay. So suppose in this cache line, if it is going to write A is equal to suppose 10 in this cache, A is equal to 10 is updated. A is equal to 10 is going to be updated here also. So that we call the why it is required means because of inconsistency in write ahead policy and write back, there may be some other processors like input output processors. They may request the same data. So there is a data inconsistency. Due to that reason, it must stall. This processor must stall until that data is updated from here to here. So to avoid this write through policy will be take place. So the write request to hit data in the cache line, that writes can be directed to cache instead of the memory. So in this write through, the information is written to cache and to the high level, to the high level memory. The high level memory, that is your main memory, is always consistent. Because of this, the main memory will be always consistent or coherent data as it is there in the cache. So it is easier to implement. There is no dirty bits, but it reads never result in write to the lower level or cheaper. So higher the bandwidth it needed, as very write needs to be sent to the main memory. Okay, so the processors may need to stall to wait for the finish of your slower memory writes. So to avoid that one, because from here to here it writes very less time, but writing here is very, it requires a lot of time. So in that case, to how to avoid that means by adding the additional hardware we call the write buffer that acts as like your cache only. So it is going to write in both the case. Let us see that one. CPU is going to write, suppose A is equal to 10 here. It is going to write A is equal to 10 in the write buffer, not directly in the main memory, to improve the performance of your processor. So this write buffer is a small chunk of memory to buffer the outgoing writes. Okay, so instead of writing it directly into the memory, the processor simply writes to the buffer and return its controls to some other operation. It is going to write, suppose perform other operation and write B is equal to 1, and the same B is equal to suppose 11 will be right and takes control. So suppose it is going to write C is equal to suppose 12 here. C is equal to 12 will be right in this write buffer. So what happens after that? This buffer plays, once it is right in the write buffer, CPU writes in the write buffer, the processor control will goes to execute the other operations, but your memory controller will manage to update these values. A is equal to or write back to your main memory from your write buffer. A is equal to your 10, B is equal to 11, and C is equal to 12. So this side operation will be managed by your memory controller, and this side operation will be managed by your processor controller. So like that, it will reduce the miss rates and increase the hit rates. How? Okay, so in this case, the processor can continue when data written to the buffer and allowing the overlap of your processor execution with memory updates. So the full write buffers will still cause some the processors to stall. So it requires the flushing. It requires the flushing. So when it is going to be, the flush means when to flush the data means there are two ways to do. One is you are frequently flushing, another one is you are non-frequently flushing. The frequently flushing, we call it as your aggressive flushing. Aggressive flushing that reduce the chance of cycles due to full write buffer. Okay, so that means in this write buffer, all the frames are frequently flushed out. In some other case, in conservative flushing means the write combines more likely, the entries stay around the longer. Okay, more likely, one or two frames, only the selected one will be flushed. Remaining still in the write buffer. So what to flush? That means you can select flushing of a particular entry. Either only one should be particular entry will be flushed out from your cache. Suppose if you have, in the write buffer, if this is a particular entry of this your cache line, only this can be flushed out, or up to the entry point, or flush everything below the particular entry. Means suppose up to this point, below all these, keep these for their further use and remove all these or flush all these from this case. Or sometime you can flush all the cache line which are written in the write buffer to out. So this is the write buffer flush pulse. So in actual CPU implementations, users can simply a part of the memory to be write back and write combined or uncached. So in the uncached memory, it behaves like a pure, when there is no cache, then it is a pure write. You can simply going to write in the main memory as there is no cache. So it is going to write. In this case, the write combined memory has the weak coherence, which may affect the program correctness if used for the normal data access. So in the previous case, we have seen if there is a write hit. If there is a write miss, then what happens? If write miss, so CPU try to write data into your cache, but that cache line is not there in the cache. Then we say that it is miss. It is going to write, that is miss. When it is miss, what happens then? It must allocate, the write allocate comes into the picture. Write allocate. So what happens, whatever the missing is there in this cache, for that, it is going to fetch that cache line from your main memory, which is, suppose in our example, you are taking A, that will be fetched and allocates. Okay, fetch and load into your cache, This process we call the write allocate. So once it is brought into your cache line, then your cache will be write your A. Suppose A is equal to 10 is there, that is going to be write A is equal to 10. So it is in write allocate means a cache block or the slot is allocated and the write message from your main memory to cache, and after that the standard write hit action will be take place. In that it is going to write A is equal to 10. So your write miss is just like your read miss. When it is going to read from here, when the cache line is not there, that read request forwarded to your main memory, from there it is going to bring, right? It is just like that. It goes well with the write back. This write allocation goes with your write back. But if there is no write allocate, when there is no write allocate means what? If there is no cache, there is no cache. The write message do not allocate any block. It only update the next level, that is the high level memory. So it is directly going to write in the main memory, because as there is no cache, there is no cache. So this is the write message. So based on the previous discussions, let us see some case studies of the modern processors. The modern processor, Intel, the Kaby Lake processor, is having 3 caches: level 1 cache, level 2 cache, and level 3 cache. As we have seen that to solve the structural hazard control, structural hazards, we have seen that L1 cache is divided into L1 instructional cache and L1 your data cache. L1 data cache. So this Intel processor is having L1 cache. That L1 cache is using for instruction. It is using 32 kilobytes, 32 kilobytes per core, and it used the cache associative memory, that 8-way set associative. In 8-way set associative means for every set is having 8 ways: 0, 1, 2, 3, 4, 5, 6, and 7. It uses 8 ways for access. And it used the L1 data cache, that is size of your 32 kilobytes per core, and use the 8-way set associative. Okay. Then the next level cache is your L2 cache. This L2 cache is unified cache again, and the size of this unified cache is 256 kilobytes per core, and it used the cache placement policy, that is 4-way cache placement policy. 4-way set associative cache placement policy. Then the next level cache is your L3 cache, that is outside or at the edge of your core, that is L3 cache. It uses this, and we call this L3 cache your shared cache also, because multiple cores can, core 1, core 2, okay, they can use the same cache, that is shared cache. It use the size of this one is 2 megabytes per core, and use this 16-way set associative. So another processor called AMD Zen processor, it uses the L1 cache size is 64 kilobytes per core, whereas your Intel is 32 kilobytes per core. And for data cache, for L1 data cache, it uses the 32 kilobytes per core, and for memory, for the cache placement policy, it use the for instruction 4-way set associative, and for data access purpose, it uses the 8-way set associative. And your L2 cache is increased from, compared to this Intel processor, the AMD processor is having 512 kilobytes per core and uses 8 ways. And the shared memory, shared cache, that is L3 cache, is having 2 megabytes per core and use the 16 ways. Another processor is ARM Cortex processor. So that having only 2 caches, your L1 cache and your L2 cache, it's not having the L3 cache. So L1 cache size for instructions, the size is 48 kilobytes per core, and use the 3 set associative for cache placement policy. And for data, L1 data cache of ARM processor is using 32 kilobytes only, and use the 2-way set associative cache placement. And the L2 cache, it is 512 MB kilobytes to, range from here to 512 kilobytes to 4 megabytes, and uses 16-way set associative. So these are the 3 different processors which are having L1, L2, L3 caches. Okay. So with this, I would like to conclude the session that your cache design is finished.